Good morning, everyone. So, as introduced by Chantima, so my name is Albert. So, I'll be the presenter today. And today, basically, the topic, as mentioned in the email and the slide here. So, today, actually, we are talking about how to solve, thermal and airflow challenges in the buildings and data center with this sort of simulation tools called CFD. Okay, so without further ado, let us start. So here will be the content basically for the short sessions today. So first of all, I will go through sort of the background with you all, like basically what are the building and data challenges, data center challenges in the modern setting, and actually how do we use the CFD to solve the thermal and airflow simulations. Okay, and as well as I will introduce a little bit about the software itself. Basically here the CFD software we are using is from Ansys. Okay, and last but not least, basically the main topic today, I'll be going through the applications, the fluid flow applications in regards to the buildings and data centers. Okay, so let's first go through a bit of background sharing. So I think perhaps you all know, like lately there actually have been a lot of increasing demand for these modern buildings and the data center to first of all deliver the high energy efficiency and the sustainability goals. Okay, all this while maintaining the thermal comfort as well as the airflow performances. Okay, so if you talk about building, so you can see that nowadays, the apartments or different kind of shopping malls, getting built here in Malaysia. So actually all those buildings, the shape and the design architecture is getting more and more complex as we all can see. So all these different shapes or the geometry, the buildings, they will actually, when interact differently with the wind. So as all you go, if there's certain wind or the air flowing through the buildings, how they actually, behave will be very different. Where it varies from geometry to geometry depending on the building structure. And if you're talking about building, we talk about the aircon, right? You don't want, as let's say the hot air at the aircon latch there, you don't want it to, get recirculated or accumulated there. Otherwise, it will affect the building, affect the performance of the aircon. And then internally, you will feel the aircon is not as strong. So that is the usual pattern why we are facing these kind of challenges. Okay. Then second thing, if you talk about data center, okay, nowadays, we are talking about all the high density servers, AI is on the rise. So you need all these high performing computers, the server in this data center room. So obviously all this when it's operating, it will emit a high amount of heat, okay, from these data servers computers. So of course, the first thing you don't want it to be accumulated inside it, and then it will gonna, cause the performance of all the machines to drop, or even cause the short wire. Okay, so basically, you would like to be able to know what is the best configurations to set so that you can have the best cooling performance. Okay, so when we talk about thermal and airflow simulations using the CFD, okay, oops. So like traditionally, if you're talking about calculations, the traditional design and maybe the rule of thumb actually often very can't really predict the airflow behavior, in all this environment. Of course you can have the calculations of how much air is coming through from the fan filter unit or anything, but exactly how they react or behave around the buildings or internal space is you can't really get that. So that is why we are using the CFD. Okay, it is called Computational Fluid Dynamics, which I will explain in a minute. But the idea is that, if you talk about building, you get to use this this method to calculate the airflow around the buildings. And same thing as well for the data center. You get to see the airflow, how does the air, whether it can reaches the hot data center area. Okay. So that is the idea. But before we talk about the applications, maybe I'll just take a a minute to explain basically what is a CFD. Okay. So for those of you who don't know, basically CFD, as I mentioned, is a short form for Computational Fluid Dynamics. Okay, so you can think of it, computation is calculations, fluid, and the dynamics. So the idea is basically we are trying to calculate or study the fluid flow, the dynamics, how it flow, how it behaves, and along with all those other parameters like the heat, the mass transfer, and other fluid flow phenomenon, basically by solving the sort of the mathematical equations. Okay, but of course we won't go deep into the theory, but that is the general idea. We are using the computer to solve some equations so that it gives you the data such as the velocity, the temperatures, or if you have different kind of gases, we can check what is the concentration as well. And of course, some other applications such as the turbo machinery, the turbine rotating, or even, nowadays, it could also simulate the flow and the structure interaction. Here is like a tank, water sloshing, then they will actually cause the stress or the, deformations on the structure itself. So all this can be, simulated within the CFD itself. And just to talk about the software quickly, basically, as I mentioned, we are using Ansys. Basically, Ansys is like an American software, so it has been widely used in the industry, for all the simulations related. Okay, because we purely focus on the simulations tools, and within the company, the software itself, it has a comprehensive set of the simulations tools. And for just give you a glance, basically these are the products that they have within the Ansys portfolio. You can simulate all the different kind of physics, from structure to electronics to even optics design. But of course, today the main thing I'll be sharing is basically on the fluids. Okay, so the software itself is Ansys Fluent. Okay, so again, this is basically a industry leading all-purpose kind of CFD tool. Basically is used to simulate all kind of fluid flow applications. Okay, like insert a few examples here. In the automotive, you get to solve the dynamics, aerodynamics, the motor, the battery cooling, all those kind of things. Energy industry equipments, chemical processing, mixing tank, even high tech as well. Nowadays, you talk about the heat sink, all the PCB board, thermal distributions, even in aerospace, and many other more. Those kind of things that involves fluid flow, you can actually use the CFD tools to simulate it. Okay, and just to give you an idea, basically when you talk about CFD simulation, that is actually the workflow. Okay, it of course here I'm using the Ansys Fluent as an example. So of course we are using the interface, but even CFD in general, regarding of what CFD's tools you are using, it will be actually using this same workflow methodology. Okay, so basically you can think of it as like maybe 4 big steps. So basically starting, you of course, when you talk about simulating building or data center, you will need to have your model. Okay, so this you can model it in your other, CAD, the conventional CAD tools, or even within the Ansys itself. Okay, once you model it, then you will apply some sort of meshing. So sorry, the meshing, so you have the grid, so that is where the data will be stored, across the space or across the component itself. Then after that, you basically do the pre-processing is what we call, but basically this is where you set up your airflow or some other things, where does the air come from, and then where does your air go out from. Okay, what is the velocity or the mass flow rate? That is where you're telling the software, so this is how I want to input my flow. Okay, then later on, if we do the calculations, once the calculation is done, then that is where you extract your results. So you can check exactly like the airflow, how does it flow in the various tool, like streamline or in vector arrows, those kind of thing. Okay, so overall, in one glance, that is the sort of the short introductions to the background and the CFD itself. Okay, now I will actually just want to go into some applications, namely on the building and the data center. Okay, So if you talk about building, of course, first of all, as I mentioned earlier, you need to have the geometry model. So the model itself, uh, as you can see, so I'm using example just like let's say you are trying to model certain building, okay, on to calculate the airflow surrounding it. Of course, now I'm using just an example. You can actually extract the layout, let's say from Google Map. You get the vector, okay. So this kind of thing here, let's say I extract the outline of the building, and then inside this is the Ansys modeling tools, okay? Or maybe, of course, you can do that in other modeling tool as well. So after that, you basically just try to extrude or build the model itself, okay? So this is one of the example of the workflow. But of course, if I talk about if you have like the layout or the blueprint of the building or new constructions, of course you're gonna have that. So from there you can also draw, or model it in your modeling tools. Okay, let's say if you're drawing from AutoCAD or some other software 2D drawings, then from there you have the dimensions, then you have the shape of the building, then you can actually just model it and then extract it out. Okay, so that is the geometry side of things. Then with that, basically you will do the simulations, right? As I mentioned, first of all, you're trying to simulate the airflow pattern surrounding the building. So in this particular example, you can see the different colors that corresponds to different value or magnitude of the velocity, how fast it flows. Okay, so why we need to study this one is because you need to identify if there's any dead spot, like sometimes there could be no air flowing through here. So here you can see red color being high velocity, and the blue means low velocity, or flow is not flowing at all. So you can see, let just take this as an example. You can see basically the way the wind interacts with the building is like, let's say the wind's blowing here. You can see that there's a lot of air flowing here, but because of the complex way it interacts with the building and then the vortex, okay, so it creates like the empty sort of low air velocity regions here. So from there you can get to see if this is ideal or this is not good. Otherwise maybe this area will be very hot, or if you put aircon here, then that means there's no fresh air coming in here because of the way they interact. So that could maybe potentially cause some problem, right? Okay, because the hot air not getting out of here because of there's no fresh air flowing here. So that could be an issue. This is why you need to simulate this kind of the analysis. Okay, so just to give you a detailed look, basically we talk about the aircon. This is what I mentioned, right? If you have like an apartment, like a high-rise building, obviously the aircon is gonna be installed in every unit. So on every floor, normally is this kind of outdoor unit where it discharge the hot air, so you can have the cold air inside the room, right? So this is the outdoor unit that discharge the hot air out. So obviously the idea is that you would want to have like a big enough space where the fresh air can just take away the hot air when it distributes to the higher region in the sky or something. And would not want to be you will not want the hot air to be recirculating around these regions, because if the hot air get recirculate, like I mentioned, let's say around here, then you don't have any fresh air, and the hot air is just gonna get recirculated back to their own machines here, the unit here. Then eventually, once the ambient temperature is raised enough, let's say to over the critical temperature, let's say 42 degree, then it's going to cause the performance of the unit to go down, and sometimes even shut down as well. So in that case, it's not ideal, because you will feel that your aircon inside the room is not really pumping enough cold air. This is basically because your hot air outdoor unit is not really performing at the optimal condition. So we want to avoid that, but there's no way to tell if you don't do these kind of simulations, because as I mentioned, you don't know how the airflow react. You know how much the air discharge from the unit, but you don't know how the other air wind interacts with it. So that's why it's very important if you get to use the simulations to simulate this kind of thing. Okay, and as I mentioned, those just now, the two is one of the example, the contour, but of course you can also see in arrow forms. So like you can see here, this just two example, like these two building interact together. You have the wind blowing from left hand side to here. So you get to see, okay, like how the arrow, I mean the air flow move. So in this example, you can see that there's actually the air moving here, but here is more like there's a vortex where the air is like because of the shape, once it hit this edge of the building, then it was just gonna recirculate. I mean, sort of creating like a vortex shape. So you basically what it's saying here is basically you actually have a very like empty, velocity flow area around this edge of this side of the building. So again, you can see this kind of effect through the simulations results. Okay, so again, you talk about the buildings, right, and the wind effect. So obviously with the simulation, sometimes during when you're doing a building design or anything, uh, normally, the high wind might, I mean, the strong wind does not necessarily just come from one directions, right? Like it could be from northeast, southwest, or even some other intermediate directions. So of course, normally you simulate the worst case scenario. Okay, let's say the wind is coming here at what meter per second magnitude. But normally, the idea, because we are using simulation, so you can also simulate all different I mean wind configurations. Let's say coming from different directions, then you can sort of analyze all together how does the wind interact with the building. Let's say from this direction or that directions. Okay, then you can sort of plan maybe plan the cityscape or the design or the positions of the building much better. Okay, in that sense. And of course, we talk about building just now, we talk about the aircon and all those things. And also importantly is also to the pedestrian or basically the people surrounding it, because you don't want that area to be have strong wind or very like a hot air getting that area. Okay. So same thing, you get to simulate this kind of streamline effect. Then you can study the interaction between the wind flow and the urban street. This is basically to sort of to ensure the pedestrian, uh, feeling more comfort, not like there's going to be a very strong high velocity wind hitting you. Okay, especially during those let's say monsoon season or wind season. Okay, and in terms of office building, there's gonna be a lot of people walking, let's say on the open space area. So obviously you will have the outdoor unit discharging heat as well. So from there, by doing this kind of simulations, you get to know basically if certain area is getting too hot, let's say in the walkway here. Right, then if is that the case, then maybe you have to think of a way to shift or put the outdoor units on other places. Okay, so by having this kind of thing, it gives you the insight, so you can better install or configure the setting properly. Okay, and moving like previously we talked about the outdoor space, right? So same thing for the indoor space. Let's say in the room, in your living room, or later on the data center, we are talking about the flow inside the room or inside the space. Okay, so the flow, I mean the modeling side of things is similar. Just now you're modeling the building, right? The airflow outside the building, but now we are modeling the internal space of the room. So you can see that this particular example, maybe it's like a room. Then of course there's going to be door, window. Of course you can model it if the air is going out, but most importantly, we are modeling the the fan unit or the aircon. This is where the air is gonna come in, or maybe the air will go out. Okay, of your aircon unit basically. Okay, so from that you get to see the result as I mentioned before. You get to see the temperature inside the room, the airflow velocity. Let's say here you can see actually obviously this aircon is blowing I mean is blowing the cold air coming down here, so you get to see the air is actually coming here. And of course there's some other tools like streamline this. Basically you can just trace how exactly the air flow it go down and then go down. After that, then where does it go? This is the sort of like a tracing of the streamline. You get to see how does the air flow spread through the room, whether it covers all the spaces or there's some corners where the air, does not reach. So that is one way to look at it. You understand your airflow. I mean, the position of the aircon, then this is the flow, then maybe you can better position it for if it doesn't reach certain area, okay? Then, of course, we talk about indoor, obviously, that aside from the machines in the data center, there's going to be, people inside the room, right? So sometimes when we talk about the simulations, airflow inside the building, internal space, you talk about what is it? The comfort as well, whether if it's too cold or if it's too hot or if it's too humid, right? So take this example, you have let's say the meeting room setting, you have people sitting here, and then of course there's going to be aircon and the outdoor, I mean the outlet. Okay, you get to evaluate the temperature as usual. Then from there, you can also take one step further, basically to try to do the thermal comfort analysis. Okay, so when we talk about thermal comfort analysis, that in setting there's like a two-way. One is like if you talk about just humidity, the airflow, we can calculate the humidity. Basically, it's just the amount of water vapor inside the air. Okay, so but basically in the thermal comfort, there's more in that there's this standard index is what we call PMV and PPD. PMV means the predicted mean value. Basically, to sort of like a scaling to see how what is it the people feeling, whether it's comfortable or it's too cold or it's too hot. Okay, then the PPD is like a predicted percentage of dissatisfaction, just basically just how they feel about the air, whether it's satisfied or not. So again, I won't go deep into the theory. Basically, it's just a scale, it's just a parameter to see whether the people are feeling comfort about it. Okay, so if it's the PMV, you can see here, generally we will want it to be in the neutral, the zero area as much as possible. So you can see that maybe in this area where people is sitting, so actually it's feeling actually more comfortable because of the way the temperature interacts, okay? And PPD here, you can see that this is about dissatisfaction. So the higher the value, the more dissatisfied. So you can see that here, the people are actually feeling more better, okay, with the humidity, the temperature, and the overall flow inside the room. Okay, so that is the thermal comfort side of thing. Okay, then last but not least, I will just want to go to another space, which is on the data cooling. Okay, data center cooling. So again, essentially the concept will be the same, like just now I introduced the indoor space. So, but we talk about indoor, there's going to be people inside. So we analyze the, thermal comfort. But obviously in a data center, less of a people inside, but more of the machines, the data rack, the server, right? So in terms of modeling, again, it's the same concept. You model the space itself, and then you of course you're gonna have the now you're gonna have the what we call heat source. The rack or the data server is gonna be emitting a lot of heat, right? So you gonna have to model that. And then as for the airflow side, of course you're gonna have the fan or the blower, the vents as your air supply or the inlet outlet in and out through the in and out of the data center room, right? So of course you're gonna model that. Okay, then of course there could be other equipments or non or what we call it, like it doesn't really generate any heat, but it is still like a very big, it might obstruct the airflow. So if those object is there, then you can also model it inside, just that as like a non-heat object, meaning it doesn't cause any heat, but it's just there to maybe block the airflow. Okay, so again, you get to simulate the same thing we talked about in the past few slides. You get to simulate the temperature, the streamline, and then of course humidity as well. Sometimes if the machines is very humidity sensitive. Okay, so of course the idea you get this kind of data, you want to avoid the hotspot in the data center. Okay, you want all the aircon to be able to reach the all the data racks, okay? And of course, you want to maintain sometimes acceptable moisture level, okay? So once you have all this, then you know that, okay, how your aircon is going to perform inside the data center. Okay, whether it's really able to cover all the data center or not, or there's some area where the air is harder to reach. Okay, so you can maybe positions your aircon differently. Let's say move it to somewhere closer, or actually install more aircon. Okay, so with those things, obviously, one when you talk about data center, you also need to develop actually fail safe or the action plans in case if the cooling system fail. Okay, so maybe you're talking about emergency fan ducting or emergency aircon unit. Okay, so those scenario, obviously you can't really do it in the actual term. Like if it happens in the actual term, then that's going to be, you know, I mean, it's very crucial. Okay, so you can, with the help of the CFD, you can actually simulate in those kind of scenario. Let's say certain fan is not moving, you can actually simulate if this or that aircon not really operating, what will my data center look like? Whether it will really accumulate a lot of heat, then 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 what is the plan? Whether I need to install some emergency ducting or escape vent or any more aircon here, just a standby. So you can actually simulate those kind of different configurations or fail-safe plan to model the scenario itself. Okay, and again, the idea is the just now is if it's the people you want to maintain the thermal comfort. So obviously, data center we're talking about the data rack. I mean the machines itself. You don't want it to get too hot, otherwise it will just shut down, right? So here is just giving an example when you model the data rack. Just now we talk about the rack as a heat source, right? This example is like normally you will average you will emit like average heat same temperature. This is like a simplified assumption. But of course, sometimes if you know more data, let's say your rack maybe is more heavy, dissipates more heat on top, maybe at the bottom, because hot air rises, right? So maybe when the bottom servers or the machines might not necessarily emit a lot of heat. Let's say it doesn't really operate a lot. You only have the machines on the top of the rack operating a lot, then that is going to be have like a gradient kind of a temperature scale. Okay, so you can also model that as the heat source, you know. So basically it gives you more customizable ability to model your rack this thermal distribution more accurately. Okay, again, you see this kind of air streamline port basically to see the air con, that means the airflow, whether it reaches or spread out to covers all the area of the data center. Okay, this is also that you can check whether your data rack, I mean temperature, it is still within the recommended range. Okay, so then, of course, data center just now is the simple kind. Of course, nowadays there's more and more different type of data center. So let's say if you have a larger scale combined kind of data center facility, let's say in those, let's say you talk about NVIDIA or some other big server, okay, kind of data center, or normally they comes in like a big space and then all connected together. Okay, so that is much more crucial because you need to ensure surely that this all aircon can cover and make sure the temperature of every area of every corner of the data center is within the safety margin of the temperature. So obviously the scale of it, just now we talk about you can simulate the building, obviously the data center you can simulate the big scale as well. Okay, and also there are other type of data center. If you're in the industry, you know that there's this type of a raised floor data center as well. So basically the cold air is going to come down from the room aircon unit is going to blow from the bottom. This is like a raised floor, so your rack is going to be here, then the raised floor here is going to have like a perforated, I mean the plate with the small holes that allow the air to come out. So basically it just gives you like a more smoother flow to the whole cold air from the bottom to sort of cool down the hot air, and then all the hot air rises and then it will move to this area. So that's just the sort of the trending configuration. Obviously, you can simulate that as well as I show here. This is an example. So the hot air is, I mean, the cold air is coming from from the beneath the floor, the raised floor, then it will just cool down the data rack, and then all the hot air you are seeing here is on top. Okay, so just a summary, today we actually just share about the thermal airflow challenges faced in building and data center applications. Okay, we talk about the modern challenges. Okay, then later on we also introduce basically the idea of putting the CFD methodology into these kind of applications, so you can actually simulate the airflow to solve their challenges. Okay, and in the building and data center applications, basically in a nutshell, this the CFD basically allows you, first and foremost, you study the airflow pattern around the complex building shapes or the data center configurations. Okay, by doing this, you get to identify the hot air recirculations regions, or even evaluate the temperature distribution. Is it too hot, or is it within the safety range? Okay, or if there's any hot spot there. Okay, of course, machines, if you talk about we want to simulate that so that we get to achieve a good thermal comfort within the space for the people, or even acceptable moisture level for the machines. Okay, and with that, the idea is that by doing all these simulations, if you get to see if your design or the configuration is meeting the standard or not. Otherwise, you can just change the configurations and simulate again until you obtain the most optimum design on the configurations. Okay, so I think that would be my presentations for today. So thank you for listening.